Hello, this is Jungsu An and Chi-Hoon Lee from Line Plus AI Hub Dev Team. Today, we would like to share the problems we encountered while operating the agent harness and how we complemented them. I will first explain the common picture for using harness in the first part. Rather than delve into the detailed implementation our team uses, will be discussed later to understand the basic perspective for hearing the detailed implementation. Please consider this as an overview of the concept. Next, Chi-Hoon will speak. Our team. In fact, I will explain in detail the structure in which harness was applied. Let me briefly introduce ourselves. We are developing systems and platforms that apply AI technology to actual services and internal work environments. Currently, there is a project called AI Friends at the top of the Line app chat room and operating. In today's presentation, I will introduce what kind of problems our team is solving with AI. First, to very briefly explain harness, we will view this as a structured work path where the agent performs its tasks. If you ask the model to fix the failing tests, then which file you should look at first? What tests should be run? It is all ambiguous as to when we can say it is complete. Therefore, the model makes a reasonable guess, but the speculation does not always align with our team's standards. The harness is, to reduce this ambiguity, to combine document tool verification criteria, records, and so on. It plays a role in creating a path that agents can follow. In this slide, it's not just the model itself, that the environment in which the model operates is important. I will just briefly touch upon this point. According to the definition in LangChain, we propose to view an agent as a model plus harness. This means that everything except the model should be seen as a harness. The model performs reasoning, generation, and selection. However, for actual work to run stably around the stage, give information, connecting tools to create a workflow, and verify, we need an environment that prevents risks. So, I'm going to call this surrounding environment a harness. Last year, we viewed the agent as the central component. There is a model, and there is a runtime where the model runs, and there is a context and tools to refer to. In other words, an agent could be described as model plus runtime plus context plus tool. The coding agents we are discussing this year are one step further, moved forward, including the order of operations, when to stop, what to verify, and how to prevent risky actions, while enhancing the environment around the model. We call this environment harness. We have started calling the work of enhancing this environment harness engineering. The important thing is that the harness, not some hidden ability inside everyone, but rather it refers to the working environment created around the model. What does it mean to pave the way? It does not mean hard coding the order of actions on the stage. What about models? We still make that judgment. However, which document to look at first? Which procedure should repetitive tasks follow? What tools can be used? You will be given an environment such as how to check the results. If you ask Q, rather than creating a single, fixed route, it is closer to creating a road network with collection points and lane guides. Just get a feel for it. Specifically, how each gate operates. We will look into this in more detail later. the actual harness is, rather than a single massive device. It is created by gathering several small components. For example, instructions that tell you what documents to look at, a procedure that guides repetitive tasks, the tool that actually performs the action, checking the results, and there is a record of the progress. Here, just note that these materials exist. Lee. In the latter part, these constraining elements, let's look in more detail at how they are integrated into operations. The model ultimately selects the skill. However, choices are not made completely in a vacuum. Depending on what skills are visible, how clear the explanation is, what context is provided, and what feedback is given when something fails. Follow? The quality of everyone's choices changes. So harness? It's not about making judgments instead of the model. It is closer to creating a working environment where better judgments are more likely to be made. Good judgment does not come from within the model alone. It is also part of good judgment to see what choices look like. Until just now, we looked at what skills the model chose. Here, I will briefly define the term skill. I would say it is a procedural task that repeatedly performs skills. For example, how to fix a test, API specification, such as how to analyze failures, or how to write release notes. It can become a single skill. The model sees the request. It selects the most appropriate skill among several skill candidates. However, another question arises here. Will we create this skill and working environment anew for each project? Or whether the team will create it in a reusable form? We are solving this problem with the concept of a plugin. The plugin is. This is an official term that exists in both OpenAI Codex and Cloud Code. Of course, the implementation of the two products is slightly different. The Claude Code plugin is Skill Agent Book. It's closer to an extension package, including MCP. The Codex plugin it is closer to a unit that deploys skill integration MCP in the form of a reusable workflow. So here, rather than focusing on implementation differences of specific products, I will focus on common concepts. We will consider a plugin as a packaged unit that allows teams to install and share the harness they created. For example, let's consider the task of modifying a polling test. You can define separately what logs to view, what tests to run, and what to consider a pass for each project. However, if we do that, the working methods and verification standards differ for each project. Therefore, we have adopted a skill and path-based verification procedure, such as fixed following tests. We bundle the necessary tools and context together to create a plugin. Then, even if the projects are different, the same work procedures, you can reuse the same verification criteria. In other words, the plugin it can be seen as a unit that shares the work methods verified by the team, rather than simply adding features. A good harness requires three main things. Firstly, we need to have predefined criteria for what constitutes a pass. Secondly, we should not just trust what the model says it has completed, but there should be a separate verification process to confirm it. Third, with the next task, so that it can continue. The progress and basis of judgment must be recorded. These three things are necessary for the agent to, going beyond merely generating answers. You can work repeatedly using the same criteria. A harness is not a structure that provides a single answer and then ends, but rather is closer to a loop. The agent acts, confirms the results, records the content, and these records then influence the next action. The significant change is not whether the model said it was finished, but rather, this means that the standard changes to whether there is remaining evidence that can be interpreted in that way. This is the general overview I wanted to present. Now, Mr. Shiwu will explain our team's advanced harness. So far, we have looked at the common foundation that allows agents to survive long tasks. From here, we will look at the gaps in common harness setups that our team actually encountered. What kind of things would there be? First, there's static skip fold. The harness engineering that is often referred to these days assumes a static environment. The goal is to handle all task types with a single harness. It becomes awkward if the prototype and the operational code pass the same verification. Second is the soft gate. When we provide the agent with, instead of prohibiting an action, it might display a warning and proceed method. It's over when a person says, "I understand," and moves on. Third, there is the drift between spec and code. Requirements or specs change, and refactoring is frequently done. Static spec documents can be problematic. As PRs are merged, the specifications increasingly become inaccurate. Fourthly, the lack of self-evolution. When the specs are wrong, we write them from scratch every time. This is because we don't know the history of what has been implemented and changed. We have addressed the 4 gaps we saw earlier with 5 layers. Due to that flag. Briefly, if I may speak about the design principles, from the inside out, the inner part is human. It is a gradation of degrees of freedom and enforcement that machines compel as we move outward. We will look at the 5 layers one by one, and then delve into them slide by slide from the next slide. First, it is a spec harness contract, before coding. Human and the agent. This is where we meticulously document the company's standards. Secondly, it is a multi-agent review, each with a different model and a different perspective. The subagent checks the same changes against different criteria. Third, within the runtime harness, a sandboxed runtime harness that is dynamically generated during the operation. This is a form where customized harnesses collectively cover various requirements. Fourth, we have a hard gate. We actively use hooks to prevent the model from passing through the gate in advance. We enforced these rules so that they could not be ignored. Lastly, the 5th point is self-evolution. We have strived to automate the process of fixing the spec when it fails due to requirement changes, refactoring, etc. What we'll look at in Layer 1 is the order. Instead of writing code first and then setting the acceptance criteria, it's a way of accurately telling you what the path is. If we agree on the passing score first, the human data reviewer will then, they look at the same criteria. The file containing the contract is manifest, and the spec manifest run.setch file leads to the actual execution. The spec. If we define what a pass is, you can think of manifest as a map that connects which harness lane runs, which run shell file for verification. At level 2, we provide various models with the ability to utilize them. The same changes. Claude 3 types of subagents. The CoderX review agents concurrently observe multiple items. The reason we use 2 models together is because their blind spots are different. Our team made this decision because we found that while token costs are high, the cost of missing bugs is much greater. Let's learn more about the runtime harness we will examine in Layer 3. The runtime harness. This refers to sandbox verification attached to specs and code, which the agent directly runs while working. You can think of it as a dynamically generated agent verification environment. If you ask what's different from existing CIs, it's not a CI that runs and ends, it grows during the task, not someone else running it for you. The agent creates and operates it on its own. It becomes impossible to simply write code and not run validation. The reason it's runtime is because we need to verify things that can only be known by running them. This is validation that we encountered while refactoring actual service integration, parts that diverge as requirements change. This is because we cannot statically cover all of these things in advance. Therefore, we added another runtime harness layer on top of the static gate. This is a method where two automatic checks are attached before and after each time the agent executes a command. You can think of it as the system handling everything on its own without human intervention. The hook attached before is a gatekeeper. The command is checked first before it is actually executed. Has the review and verification been passed? If not, it will be blocked on the spot. For example, if you try to modify or generate code without a design document, the command simply won't work. Secondly, this is the record sheet. When a command ends, the result is written on a line, and the latest status is continuously updated for the next check. The key is that these two run regardless of the model's judgment. Even if the model judges, let's just skip this one, without any input from a human, because it was enforced with a hook, it will always be caught. Up until now, if the picture was of an agent passing tests laid out by humans. In this runtime harness, if the agent needs a validation harness during its work, it creates it directly. There are 5 steps in the process displayed on the screen. First, we examine how various harness lanes are structured, then assemble them and run them on site. The key here is that it doesn't end with adding validation. The next step only proceeds if the added validation passes. If it's a red light, the commit itself won't happen. So, the agent becomes both the subject being inspected and the subject doing the inspecting. In Layer 4, we discussed how the harness lane can be efficiently managed. First, line detection. You can think of each of these as a unit of validation. You can think of one type of verification as a lane. Each time, a lane turns. The result is indexed by checks. It accumulates automatically line by line in a file. When? Which branch? Was it successful? How much time did it take? Those things. It is a method of recording it as a file. When needed, these accumulated history ledgers are examined using a tool. Audit Trend looks at the flow and whether the same lane gradually slows down or frequently breaks. And the Parallel to Write tool helps us assess the cost effectiveness of our harness engineering. It shows us whether this harness engineering is effective in verification or just consuming time. This kind of verification, we separately installed tools. The key is that we don't collect the results separately, but instead record them in file form and append them so that the agent can easily refer to them at any time. I will now explain the hard gates in Layer 4. This isn't actually a warning, it's a blocking mechanism. Agent is. At the moment, it attempts to take dangerous actions, regardless of the developer's intentions. This method completely blocks the tool call itself. So, what about coding agents? It will enter its own loop, but ultimately, it will be considered a failure, and then it will seek other paths or request feedback from the user. There are several points that block it. If a review or validation fails during a commit, it is blocked. Even when pushing, if there is no design document, we block it. And when we submit a PR, we need to consider whether the harness lane I mentioned earlier has passed, and if the verification during command execution will be reliable or not. It is a system that determines and blocks such things. These hard gates. It can run on developers' local PCs. You might think, can't I just turn off the hook on my PC? However, it only operates in one's personal environment. Already, Once the developer and agent have reached an agreement after commit, push, and PR, those harness engineering are meant to be a common standard for the team and are designed to always work. Our team tried to take it a step further by creating a plugin. If layers 1 through 4 were about adhering to human-made designs, this is about what to do when the design itself is flawed. Usually, people rewrite or modify it from scratch, but this layer is an attempt to automate the process itself. I would like to highlight 2 stages in the overall flow where we put in particular effort. The first is wonder. When something needed to be fixed during evaluation, we didn't start by making a modification. Where was the spec empty that caused it to fail? What we don't know. It is a method of conducting deep interviews with user developers. This is the stage where we accurately define the problem and, afterwards, Reflect creates a revision to learn from the empty spaces. Secondly, there is equate. The proposed changes are not automatically reflected and must go through human approval once. We added 2 more things here. If a change is rejected once, it is automatically excluded from the next candidate list. We do not repeat the same proposals. Secondly, if there is no response for 30 minutes to an hour, it automatically stops, and unapproved changes are. It's a way of not being neglected. What is the core of the pipeline for automatically evolving skills? This means that it is not automatically reflected, but rather requires at least one human approval. Automation does not exclude people. The key is to make human decisions easier and to allow people to focus on those decisions and create this skill. As we created the self-evolving pipeline, another thing was added. As Jung-Soo explained earlier, a skill is a kind of work instruction that tells the agent how to perform a task. Has been explained. As a result of our operations, we confirmed that this manual, which we call a scale, changes more frequently than the specifications. Therefore, we designed and implemented the manual self-skill to be continuously improved. This improvement method borrowed 3 concepts from model training. First, I'd like to address the go. We iterate through multiple generations instead of completing the revision in one go. And it is a method that gradually reduces the number of candidates created in each generation. In the first generation, we broadly attempt up to 10 options, then reduce the number as generations narrow, leaving only 1 at the end. In the beginning, we broadly explore, and in the latter half, we focus on the most promising one. It is a method of narrowing down the direction. Secondly, this is a unit of work that reflects optimized skills immediately. If we compare it to a coding agent, we gather and reflect on the feedback at the end of each session. This is because these accumulated changes can be adopted stably. It allows for managing versions of changed manuals and skills, enabling later tracking of why these changes were made. The most important point is that all of these things are applied in the process where the agent coordinates and asks people. While creating skills, we made it so that specifications and skills can be modified together. It was a method of consolidating approvals into a single bundle rather than receiving them individually. This is because skills and specifications are a pair. A specification dictates how code should be implemented and how functions should operate. What about specs and skills? They have become inextricably linked. And what about specs and skills? This is because if one side is misaligned, the next generation will end up misaligned as well. So we'll write down the 2 revisions to a temporary folder. Lastly, by renaming the folder. Either both are applied or neither are. We did it this way. The flow we have seen so far is developers. If we were to do each one in detail, there were many steps involved. Therefore, we have introduced the same goal to this plugin. Unlike the goals of Claude Code or Codex, which were based on existing models, this goal is literally to create a valid goal for runtime harness and verification, and internally use it as a standard for the codebase. This is a method where actions are performed based on a set goal. However, this goal does not mean that the agent can simply rush ahead and code whatever it wants. If it gets stuck, it still stops. And because the standard for humans is clearly specified, even if we set it as a goal, we actively use clear criteria for people and the Ask User Question tool. If you modify a large code base all at once, it may not end in one session. Context and windows are found, and people also get tired. Complex features are. Code review can prevent you from cutting it into smaller units. The problem is that when the session changes, the memory of what the previous session did is lost. So, what happened as we moved towards the final stage was that we enabled logging in and effectively viewing logs. The key is that the agent automatically logs the "I've completed this much" handover document every time. This slide summarizes how we addressed the 4 issues raised earlier with the layers we created. To briefly touch upon this, the problem of design being prematurely finalized is addressed by the spec harness contract. We've made it so that they receive it. Secondly, the issue where the inspection only warns and doesn't block is, as I mentioned, the runtime harness and hardgate work together to block access completely. When the session changed, the problem of losing context was addressed by applying session continuity logs. Fourth, we proceeded with the self-improve pipeline for problems that the design itself could not fix. All of this is local to the harness and manifest, starting with a saved file, Claude Code, or Codex. No matter what it is used for, it is designed to operate correctly. When you fix code, you have spec code validation. These 3, they start to work somewhat independently. Over time, there are many cases where the specification is written one way, but the code is completely different. This is the moment when commonly known documents become false. If we adopt this harness plugin, the specification and the code remain synchronized, so ultimately, the specification is the code. It becomes possible to maintain a certain motivation. This slide compares the same change using 2 different paths. Number 1 is a method where you write the code first and then add verification as you go. The problem is only discovered after it has been merged. What about after? By placing the spec and harness first. It must pass the validation criteria. This is how it proceeds correctly. If we summarize this plugin into 4 messages, first, a warning is not a blockage. You must deny the tool call when you truly intend to block it. Harness comes before code. Rather than writing code and then adding validation, we must create the validation first, and the code must pass that validation. The specifications also become part of the agent's learning when the spec is incorrect. Instead of people rewriting it, they create patch candidates. It is applied with human approval. What if we use multiple models together? They become mutually secure. If Claude and Codex read the same contract, it would reduce the model's blind spots. So far, we have discussed the plugin for the harness developed by our team. There is still a lot of work for our team to do. Setting up metrics to quantitatively check how the harness has improved. The method of aligning the specifications of planning documents and development documents. Examples include various research and experiments for more efficient token usage and subagent settings. Our team is continuously considering how to teach human standards to agents and harnesses. Thank you for listening to our team's concerns about creating a stable and scalable codebase rather than a rapid development cycle.